Hello everyone, my name is Li Yixuan from the School of Artificial Intelligence, University of Chinese Academy of Sciences. Today, I'm very happy to present our work, QDepth VLA Quantized Depth Prediction as Auxiliary Supervision for Vision Language Action Models. First, let's look at the motivation. Although recent vision language action models achieve strong semantic understanding, many of them still struggle with spatial reasoning. Most current VLA models mainly rely on RGB observations. However, RGB images do not explicitly provide geometric structure information. As a result, spatial ambiguity often harms manipulation performance. This issue becomes even more critical in long-horizon and fine-grained manipulation tasks, where stable spatial reasoning is essential. So this naturally leads to our question. How can we introduce 3D geometric understanding into VLA models? There are currently several mainstream paradigms for integrating 3D information into VLA models. The first one is 3D fusion, which directly fuses point clouds or depth features into the backbone. This provides strong geometric information, but it also introduces significant computational costs and may disrupt pre-trained semantic alignments. The second paradigm is 3D injection, which introduces dedicated 3D embeddings or 3D encoders into the policy head. This improves spatial representation, but usually requires extra sensors and suffers from modality gaps between RGB and 3D features. The third paradigm is 3D projection, which projects 3D information into 2D representations. This is compatible with pre-trained VLMs, but inevitably loses some fine-grained geometric details. Our work belongs to the fourth category, which is 3D prediction. Instead of explicitly fusing 3D features, we encourage the model to learn geometric understanding through auxiliary prediction tasks. This paradigm preserves semantic alignment, avoids extra 3D inputs during the inference, and provides a more scalable solution for spatial reasoning. In addition, with the rapid progress of foundation depth models such as video depth anything, depth supervision signals are becoming increasingly stable and reliable. This further improves the practicality of 3D prediction paradigms. And our key idea is to use the depth prediction as auxiliary supervision for VLA learning. Specifically, we predict quantized depth tokens to encourage the model to learn compact and critical geometric structure information. To avoid interfering with pre-trained semantic backbone, we introduce a dedicated depth expert branch responsible for depth-aware representation learning. We also propose a hybrid attention mechanism that selectively injects geometric cues into policy learning. Together, this design improves spatial reasoning while maintaining semantic understanding. And there is also a natural question: is why do we use quantized depth instead of direct pixel level depth regression? The reason is that dense depth regression often introduces redundant low-level details and noisy supervision. Instead, quantized latent depth provides a more compact and structured geometric representation. This improves optimization stability and helps the model focus on critical spatial structure information. Empirically, we also observe that quantized depth supervision leads to better downstream manipulation performance. And this slide shows the overall architecture of QDepth VLA. Our framework mainly contains three key components. First, the dedicated depth expert branch models geometry-aware representations. Second, hybrid attention selectively routes depth information into policy learning. Finally, the model jointly performs action prediction and depth prediction during training. And then I will briefly introduce the hypertension mechanism. The key idea is selective routing of depth information instead of allowing an restricted interaction between all modalities. Hyperattention controls how depth features interact with semantic features. This improves cross-modal alignment and prevents noisy geometric information from interfering with semantic reasoning. As a result, manipulation behavior becomes more stable and spatially consistent. We also evaluate our model on several benchmarks and the real world and first we evaluate QDepth VLA on the liberal benchmark. Compared with existing methods, QDepth VLA outperforms both 3D KVLA under single view settings and COT VLA. More importantly, compared with OpenPy0, we achieve a 8.8 percentage point improvement on spatial tasks. This demonstrates that depth supervision significantly improves spatial reasoning ability. We still observe slightly lower performance than spatial VLA on some tasks. This is mainly due to limitation of the base model and residual errors in depth estimation under challenging scenarios. We also evaluate our method on simpler benchmark. On stack block tasks, we achieve a 23.8 percentage point improvements compared to OpenPy0. Overall, our method improves manipulation performance, especially on pick and place tasks. However, depth enhancement policy learning still has limitation in tasks with extremely subtle geometric differences, such as closed drawer or in scenario with severe occlusion. These cases remain challenging for current depth estimation methods. Next, we come to the real-world manipulation. We further related our method in real-world robotic experiments. The task includes pick and place and stacking scenarios. Compared with baseline methods, QDepth VLA demonstrates improved robustness in cluttered and complex environments. We also observe more stable manipulation behavior during execution. This result suggests that quantized depth supervision can transfer effectively from simulation to real-world settings. What's more, we look at the ablation study. We analyze the contribution of each component in our framework. The results show that the depth expert contributes the most to the performance improvements. We also verified that latent depth prediction performs better than pixel-wise regression. In addition, hybrid attention helps stabilize policy learning and improves cross-model alignments. Overall, the components contribute positively to the final performance. And computational costs compared to OpenPy0, the parameter count increases from 2.606 billion to 2.924 billion, which is about 12.2% increase. And the depth annotation is generated offline and takes approximately about 4 hours. And when it comes to deployments, the inference overhead is relatively small. Finally, as a conclusion, we propose QDepth VLA framework with quantized depth supervision. Our experiments demonstrate that depth supervision significantly improves spatial reasoning ability, and that the quantized latent depth is more effective than pixel-wise regression. And last, for future work, we plan to explore more efficient 3D geometric representations and future depth prediction for enhanced spatial reasoning. And thank you for your listening.